This is video 2 of looking at constant velocity problems. And I apologize, I listened to the very beginning of my first video and I was not very perky. So I'm going to try to sound a little perkier in this one. So anyway, so we're going to look at this example. All right, so this one says we're going to start out with a velocity equation for the path of an object. I don't know why I'm doing this in a different color. Velocity equation for the path of an object. All right, and this says that xy, all right, which is going to be the position of an object, is going to be equal to 1, 9, vector 1, 9, plus t, which will represent time, times the vector 3, negative 4. And that 3, negative 4 is our velocity vector. And it says that t is going to be time in seconds, times greater than or equal to 0, and the distance units are going to be in meters. So I just want to point out again that this represents position, initial position, and the units there are going to be meters. Right? This is going to represent final position, and those units are also in meters. We said that time was in seconds. And then what we said about the velocity vector before is that this velocity vector will always be in whatever units we're moving, which is meters per unit of time. So because our time is in seconds, this will be in meters per second. And so if we just do a little bit of unit analysis here, we can see on the right-hand side we're going to have meters plus, and then we'll have seconds times meters per second. So those will cancel out. So we'll have meters plus meters, which is meters. So that confirms that this will be in meters. Okay, so this says find the object's initial position. All right, well, the initial position for part A, we already know, is going to be the ordered pair 1, 9. Right, because that's what this initial position vector represents. All right, then it says plot the path of the object for time equals 0, 1, 2, and 3. So what I'm going to do is make a little table of values here, and we're going to work out these values. So we're going to do time, and the time is going to be 0, 1, 2, and 3. And so if we want to work out the path, we need to work out what the positions are, what the x and y positions are going to be. So up here, I just want to rewrite this vector equation in parametric form. So we can see that x is going to be equal to 1 plus 3t, and y is going to be equal to 9 minus 4t. So I'm just going to write that here. So x will be 1 plus 3t, and y will be 9 minus 4t. And so then we're just going to substitute in. So if I sub in 0 for time here, I get 1 plus 3 times 0, which is just 1. And then here I'll get 9 minus 4 times 0, which is just 9. And then I will let you confirm the rest of these. If I sub in 1, I'm going to get 4, 5. If I sub in 2, I'll get 7, 1. 3, I'll get 10, negative 3. So we want to plot that. So we're going to start out at 1, 9. Right? And notice that that's going to be at time equals 0. And then we'll be at 4, 5 at time equal 1. And then we'll be at 7, 1 at time equal 2. And at 10, negative 3 at time equal 3. Right? And we can see, looking at that we're going over 3, 1, 2, 3, down 4 each time. 1, 2, 3, 4. Over 3, 1, 2, 3, down 4. 1, 2, 3, 4. Over 3, 1, 2, 3, down 4. So you can kind of confirm that. So we see that the path of this what are we talking? It's just the path of an object is going to come along this way. So it's starting here, and we can see exactly what direction it's moving. Then it says for C to find the velocity vector of the object. Well, we already said the velocity vector is represented by this vector right here. And so that's going to be the vector 3, negative 4. And I want to emphasize something about the velocity vector compared to the direction vector. So the velocity vector is going to be this specific vector, right? Because in 1 second, it's moving 3 to the right and 4 down. and that's specifically that movement. And it's going to be moving at, a total distance of 5, just like we had before. But the direction vector for this line, there are infinitely many direction vectors you could write. I mean, we could write 3, -4, but we could also write, 6, -8, right? That would be a direction vector for this line. Or we could do another multiple, 9, -12, or something like that. So all of those would be direction vectors, but the only one that's the velocity vector is this, because it's per second. It's moving, to the right 3 and down 4. Okay, then we want the object speed. Well, we said that the speed is going to be the magnitude of that velocity vector. So the magnitude of 3, -4, which is just going to be the square root of 9 + 16, which is going to be 5. All right, and then the units are, we already said, meters per second. All right, and then for E, it says if the object continues in the same direction but increases its speed to 30 meters per second, state its new velocity vector. So if its speed is 5 right here for this vector 3, -4, then hopefully it makes sense that we would need 6 of those. All right, in other words, it would go 6 of these little segments in 1 second. And so that means that one way we can think about this is that we would need 6 times the vector 3, -4, which would be 18, -24. All right, that would be its new velocity vector, because it would move this in 1 second. All right, or remember the other way that we had for doing these is if you have a vector, if you have this vector 3, -4, and we know that the magnitude is 5, if I take 1/5 of that, that would kind of shrink it down. Instead of having a magnitude of 5 like this, it would have a magnitude of 1. And then what I can do is take that vector and multiply it by 30, because that'll take that unit vector and stretch it out to 30. And so you can see that we're going to end up with 30/5, which is, again, 6 times 3, -4, which is 18, -24. So in other words, we've done problems like that before. I'm going to stop there, and we will do example 10 in another video.